Devajyoti, Devajit, am I audible? Am I audible? Yeah.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes.
You are audible.
From first semester students, anyone?
Yes, sir. You're audible.
Okay. So we are going to start another interesting hands-on demonstration of tutorial 4 of the GIAN program, Biological Cell Imaging for Diagnosis and Early Prediction of Cancer. So this is especially we will discuss on the unit using the segment and the extract the ROI region for the abnormality detection. So with me, assistant or the assistantship will be given by Shashwato Shorkar, our research scholar, PhD inspired research scholar, computer science in engineering department. So I think this session is totally a practical, and you have to know the neural network, deep neural network, with a conceptual part of each and every step of it, with introduction, importance of the nuclear segmentation in microscopic images, deep learning based analysis of microscopic cell images, and why chosen unit, nuclear segmentation from microscopic images using deep neural network, working of, that is the basic principle I think of the convolution block, demonstration of hands-on unit architecture, and how to write the program using the Python. So Shashwato will deliver this thing, and before this, you know the introduction, all these things, as we are avoiding the manual examination, and the whole world is trying to automation to detect, segment, and classification of the cell imaging, and automation using deep learning based image segmentation and enhance its accuracy also. So then, as we know, the importance of the nuclear segmentation in microscopic imaging, but can we resolve the total image processing thing in a machine learning approach and using a architecture that is called unit? But from the students, I have one question, that is, you have already completed, I think, master degree students, convolution layer, then activation layer, then zero padding, then max pooling, then flattened the image. So anyone tell me, are you know about the convolution layer? Anyone? Devajyoti, Devajit?
Yes, sir.
Okay. So Devajit, can you tell me about the convolution layer? Anyone that is you know, not a definition from the book.
Sir, the convolution layer is a fundamental building block of a convolution neural network, which applies a convolution operation to its input data, and the input data should be like grid type data, such as images, videos, etc.
Very good, very good. but I think my observation is a that is the convolution layer, that is a one kind of play with the filters, I think, isn't it, Devojit?
Yes, sir. Yes, sir.
Yes.
Filter or kernel, sir.
So and 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 using this kind of mask or kernel, you can generate some filters also, which give you the feature like edge, texture, line, while maintaining the spatial relationship. Okay, so this portion, then after this convolution, we will use some activation function. So some like ReLU and softmax, this kind of thing. So this kind of every step and their knowledge and how to write a program in Python, the Shashwata will give uh, this demonstration. So I am requesting Shashwata, please start your demonstration, please.
Okay, thanks a lot, sir, for giving me an opportunity. Uh, so,
And
here,
hope the students will benefit it. Your this hands-on and demonstration. Thank you.
okay,
Thank
okay,
you.
okay. Am I audible? Am I audible? Hello. Okay, okay. So, I want to tell about the nuclear segmentation in microscopic images, as sir told. Actually, this nuclear segmentation, why the I only choose the nucleus, because in microscopic images, the abnormality detection has been examined through these nucleus features only. Here I have written second line, the cytological analysis of that microscopic image by examined through nuclear morphology changes, which
Hello, Shashwata. Can you stop for 5 minutes? There is a technical issue.
okay. Hello, hello, hello. Am I audible?
Yes, you are audible. You can start your presentation.
Okay. So there is an actually it's represented by tutorial 4 as a tool hands-on demonstration using the microscopic image to segment or extract the suspicion region of interest from the holistic microscopic images for abnormality detection. So here is the content as introduction is as I told and then the importance of nucleus, how to segment the nucleus in that particular in that microscopic images and what is the importance it is, and then deep learning based analysis of that microscopic cell images and why to choose the unit, and nuclear segmentation from microscopic images using deep neural network, and hands-on session of unit architecture, how it is developed. Okay. Then introduction, as ma'am has been explained about the microscopic images. So manual examination of that microscopic images is time consuming and subjective. So automation is needed, and for that image segmentation enhance the accuracy and efficiency. And we are just only focusing to extract the nucleus region, which provides the diagnostic features actually. And why this importance of nuclear segmentation and microscopic images, as I have told earlier that by examining nuclear morphology, it can change its shape, size, and chromatin texture and nucleus to cytoplasm ratio for vital diagnostic indicators. So therefore, precise segmentation of the nucleus is a foundational step to extract the features for features for classification, and also reducing human subjectivity for visual screening and automatic diagnostic pipeline for large-scale screening programs. So here, this is actually a deep learning-based analysis of microscopic cell images. Actually, what is deep learning? For deep learning, it has about 3 tasks actually. First of all, the task is classification task and detection task and segmentation task. As I considered an input image, which is a microscopic image, and it passed to a deep neural network. Then deep neural network will be decide whether it will do a classification, detection, or segmentation according to the needs of the work or the research. What we do, we actually do. For classification, actually for classification tasks, the input image tells about what is the image actually, what is present in that particular image, whether it is a normal cell or it is an abnormal cell. For me, I considered a normal cell microscopic image. For that, what is in the image, it is a normal cell image. And for detection, what and where the nucleus present in the image, because I am focusing on the nucleus, because abnormality present in the microscopic images also depict that whether it is abnormal or normal. And the cancer, as the workshop based on the cancer protection from for the women. So I have considered this as a normal image. For detection purpose, what and where the nucleus present in that particular image, we focus on that, and detection gives the nuclei where it is located and draw a bounding box. And last and our task is the segmentation task, which is what and where and which pixels of nucleus present in the image, because image is based on the pixels. Pixel information gives the image visualization, actually pixel values. So where that nucleus pixel is originated, and this ROI means region of interest get extracted and segmented. This is actually the 3 tasks. Why to choose UNet for microscopic image nuclear segmentation? Because specially designed for medical image segmentation, which has been developed by Olaf Ronneberger, Philip Fisher, and Thomas Borox, performs effectively even with a limited microscopic image data. Encoder, it is actually designed based on the encoder decoder, which encoder actually extracts the hierarchical features, and decoder reconstruct that fine pixel level maps with skip connection for accurate boundaries, and pixel level precision, which provide the dense segmentation distinction in each pixel, such as nucleus or its background, and handling overlap effectively. Robust to variability, perform well even under staining illumination differences, noise, overlapping cytoplasm due to multi-scale feature. So it's performed well on that scenario. Efficient and practical. Lightweight architecture is a very lightweight architecture, enables fast training and real-time inference for clinical diagnosis use. Then, this I have considered a microscopic image dataset, which is an institute dataset as earlier lecture has been explained. Nuclear segmentation from microscopic image using deep neural network. Actually, the scenario is that this is the data set where the binary means this is the input RGB image and this is the binary output means binary ground truth, which refers that only I have shown the nucleus actually. Okay, so which I have only shows only the nucleus. Whether is the abnormal, the left hand side portion is depicts the normal subjects and the right hand side is the abnormal subjects. Then I passes these images to the model or deep neural network or whatever I have considered here as a unit. So I have passed this kind of images to unit to train, and then after during testing I have got this kind of output. So actually, what is deep neural network? Deep neural network is nothing a branch of series of branch or series of convolutional blocks actually. Some visual images has been passed through a multiple convolutional blocks and then extract the features from that particular block. And whether it is an edge features, shape features, texture features, or whatever. But for first of all, we have to understand that what is convolutional block actually, what it is. So working of convolution block. First of all, when we do convolution operation, so convolution operation, I have considered an image. I have selected 8 by 8 patch. On the basis of this, the pixel value I have been extracted. So from that pixel, I have considered 3 by 3 patch for convolution operation. And this 3 by 3 patch perform dot product with the particular filter. Yes, that filter which helps to extract the features from the images. Then how it is done? If considering that the 3 by 3 patch and the filter is also 3 by 3, then we overlap this. As a visualization purpose, this overlapping perform a dot product operation, which is a pixel wise multiplication. In filter it causes -1 and in pixel value it is 124. So 124 into -1 plus 124 into -1 plus 123 into -1 plus 124 into -1. In this way, the operation has been done, and by adding it gives me a -1, which I have shown in a red color block. Then, after that, we got that particular pixel value 8 by 8 patch convolutional 8 by 8 feature map. On basis of this feature map, not just convolution operation has been done. So, ReLU activation is needed to discard the negative values. Actually, it discard the negative values. As you can see here, where the negative is present, suppose I am considering in second column, second row, the position, second column, second row here depicts -8, which became 0 by applying ReLU. Same as considered here, -4 and -3, it became 5. So here it is actually became all 0, the negative values. Then I perform pooling operation. This is the most important thing, because after convolution ReLU must have to done. Then after pooling operation will be done. So here in the unit, they considered max pooling. Why max pooling? Because to consider the max pooling operation has been done on the max. Here I have considered 2 by 2. 2 by 2 means each feature have been considered here. Okay, then 665, 390, 363 among them which will be the greater, among considering the 2 by 2 block, 2 by 2 block, and from that block, particular block, which is the maximum pixel value, it will be extracted, which is the 665. 370, 364, 5 by 5 next, which is depicting 370 because it's the highest. Among them, 370 to 38700 is doing 387. So finally, these features has been came, and in this way, the output features of one convolution block, for considering as an example of 8 by 8 patch, I have found that particular feature for one 8 by 8 patch. Okay, next I will do the demonstration of hands-on unit architecture. This is the overall unit architecture. The name U has been came because the structure is like an U, and first of all, this part as the encoder, and from that it is decoder. Actually, what is encoder and decoder? I will explain next slide. So this is actually encoder. First of all, here the input image is passes to the first convolution block here. So this is block 1. Block 1 means these two gray color shapes has been represented at a convolution block. Okay, so and in the above figure you will see that I have mentioned it that the blue arrow, is representing convolution operation, and the dashes is a concatenation operation or skip connection, and this sky blue, deep sky blue, is an upsampling or max pooling, and hash 2 at the rate 2, sorry, at the rate 2 is the 2 times convolution has been performed, and black row is performing sigmoid aggregation function representing. Okay, then this block 1 have taking an input of size 128 by 128 by 3 as an input image size. Then it performing convolution operation. Then it gives 128 by 128 by 64, where this 64 represents the 64th number of filters, and each 64 number of filter, and each filter is performing 3 by 3. Each filter is size is 3 by 3, and this filter perform convolution operation first time and then second time, consequently 2 times simultaneously. Then it gives as detail I have written 2 3 by 3 convolution 2D operation has been done. At the rate represent that at the rate 2 is 2 convolution has been done, and 1 max pooling. Here the deep blue arrow representing the max pooling operation. So here what the max pooling operation is actually decreases the sizes about 2, means if you divide that last feature 128 and 64 is the number of filters, it remains same, but the image dimension has been reduced, which is half 128 half 64. So the after max pooling operation, next block take an input as a 64 by 64 by 64. Okay, then again these 2 blocks performing same after 2 convolution, it is about 64 by 64 into 128. Okay, because number of filters has also been increased, it's increased about 2 times. Around 64 I have considered, first of all they have considered 64, and it increases into 2 is 128. So after 2 convolution, the feature map size is 64 by 64 by 128. Details has been written as I have told, 2 convolution operation plus 1 max pool operation. Then same as it is here, you have seen that 64 by 64 by 128 had remain, the 128 filters remain same, just the image dimension 64 by 64 has been divided into half, which is 32 by 32 by 128 max pool operation. The maximizes the value and the size has been increased that I showed earlier diagram, earlier slides. So then after same operation has been done, then 66 by 2 to 256. Then after max pooling operation, there is one layer which is they have named as bottleneck layer, which is a block 5 layer, which input size after block 4 last convolution operation, it gives 16 by 16 by 512, and it became 8 by 8 into 512, where 512 is the number of filters. And then after convolution operation, they considered here 1024 filter, which is 5 by 512 into 2 times. Then here no pooling is the pooling has been ended up to block 4. After that there is no pooling operation, because pooling operation has been done to extract the meaningful features as per need. The meaningful, so no pooling operation after bottleneck layer. Then it is decoder time, which is upsampling, how it got up. So first block 6. Block 6 is the, here above you have seen that after convolution its size is 8 by 8 into 1024. So block 6 input shape will be, means convolution operation, to perform convolution operation input will be 8 by 8 into 1024. See, input size is 8 into 8 into 1024. After assembling or convolution transpose, it gives the 16 by 16. Here, the input size is becoming double, is 16 into 16 into 1024. Here, the dotted line that I have represent and tell the skip connections, which means they extract the features from the block 4 layer, as you see there. This is the 16 by 16 into 512, the block 4 final output. These features has been extracted here. So after that we concatenate the two features. After one convolution, the input the output became 16 by 16 into 1024. Here I have mentioned it. Then after that block 4 output has been concatenated or extracted from here, from the previous encoder, and then 16 by 16 into 1024 plus 512, here only means filters have been added, and it became 16 by 16 into 1536, because the dimension will remain same, number of filters will be increased, because we concatenating two output features. Then after convolution, then same after the convolution operation will be performed, where it will give 16 by 16 into 512 to get some why we are extracting this, to get some information from the encoder which will be a meaningful. Then in details I have written that 2 3 by 3 convolution operation, because all convolution operation is performing is 3 by 3 only, where 3 by 3 because the filter size is 3 by 3. Then block 7 representing input size, because this block giving an input is 16 by 16 into 512. This is the output feature map. Then this feature map taken input to the block 7 and performing same operation, and it became 32 by 32 by 512 during convolution transpose, and then concate with encoder block 3 output, which is 32 by 32 by 256, and after then convolution operation is doing 2 times, which is 32, which giving output features are 32 by 32 into 256. It's 2 times. Okay, then block 8 taking an input as 32 by 32 by 256, and by convolution transpose it became 64 by 64 into 256. Again they are concatenated with the encoder block 2 output, feature, which is 64 by 64 by 128. The features has been concatenated and it became 64 by 64 by 384. And then the convolution operation has been performed on 64 by 64 by 384. After then the output features of that particular consecutive convolution giving 64 by 64 into 128. Okay, and then after then it is block 9, which is the last block where it is the final features map which giving after convolution operation, which is an in taking an input of that block 8 architecture output, and then doing upsampling operation or convolution transpose. Then it became 128 by 128 by 128, and then it taking the output of encoder block 1 output as an input and then concatenated, and it became 128 by 128 by 192. Then performing convolution operation on that 128 by 128 by 192, then it gives the final features is 128 by 128 by 64. In this way, the whole 9 blocks has been performed in the particular unit to extract the meaningful feature according to our needs of ROI. And this is the final thing, which is an this is the encoder decoder as I've shown, and the last block 9 giving an output of 128 by 128 by 64, performing a convolution operation here also, but the size is 1 by 1 filter has been chosen because to convert it into a 1D array, and these features has been passes through sigmoid activation function, which is actually I have not mentioned the formula here. It is actually 1 by 1 plus e to the power minus x, where x is the total convolution 1D output. Here the convolution 2D is not mentioned because one time convolution operation has been done, and its name is convolution 1D, and after that the sigmoid activation function has been done. So finally we have got, after applying the sigmoid activation function, which with the help of that activation function we generate a binary marks according to our needs. You see this white region is my ROI which I want to extract as per our needs. Then here the practical explanation of that unit using Python. So here actually first 1 2 3 4 5 6 7 8 9 10 lines represent Python libraries which help to build a deep learning model. So because for that, suppose if we choose we using TensorFlow, or you can use also PyTorch, but I am preferable in TensorFlow only. So I import the TensorFlow, then whatever I need like input, convolution, 2D, is it existing only the library functions in build-up library functions in Python. Due to advancement of today's world, the library Python has been so advanced that all convolution operation you have don't need to do manually. It's already updated as a library function in Python libraries. So convolution 2D, net pooling 2D, upsampling, which is a convolution transpose, and then concatenating operation also you don't need to do manually. It's by defining that particular function, the two things will be concatenated, and then after that define process images in directory. Here this means, first of all, suppose the images have different dimensions. Suppose I have considered the data set, the microscopic image data set, each image have different shapes. So if each image has different shape, then we have to resize it into particular dimension to extract meaningful features, and it will train better. So here I have considered 128 by 128. On the basis of that, whether it's in JPG, PNG, TIFF format or BMP file. So because binary marks, as earlier lecture you have shown that binary marks has been developed in and saved it into two format, whether it is PNG or .bmp files. So uh, ground truth and the images have to consider in all of our extensions what is available in the image extensions .jpg, .jpg, .png, .tif, .bmp has been considered, and then it in sorted these two lines indicating that whether in that particular directory the images are present or not. This is using globe functions, which is also a Python library to select whether this kind of images are present or not. So how many images are there? If length of the image equals to 0, or length of the image marks path means GT ground truth is there or not. If equals to no image are found. If yes, then it will to the for loop and collecting and then resize, and if the then it converted into grayscale, the binary marks has been converted to grayscale, then all operation is done, then it whatever the information is there, it is represented in 1D array, which is x dot append img or marks, then image marks and loaded. After that, this is the process image, means I have to resize in a particular dimension, which is 128 by 128 by 3, and for binary marks 128 by 128 by 1. So for that I need to define a process to give me a fixed image dimension and fixed ground truth dimension. Then after that I have to load an image. These are all images after resizing or pre-processing operation, then loading. Loading for that particular data loading is done due to uh, taking an input to the unit. A whole image is as an input to the unit. So we have mentioned here load images and marks. Where same, these also check whether it is resized or not. Then image marks has been considered into two arrays or matrix representation, whatever. For image path, in whether there is an image or image is present or not with that particular name is present or not, and the image name will be same. If there is a different name, then you have to again rename that particular images, and then with different Python code, you have to rename it, because fixed name is better to extract all kind of images. You have to be in fixed name and fixed extension. If there is a suppose I have considered 100 images, and among that if there is a 80 images of .jpg and with different name and 20 images with different name, then it will give me an error, because it can take as an input to the unit. After that, all operation here, uh, the image pairs has been means both image pairs has been successfully, means that both images and ground truth have been successfully loaded. And after that, here is a unit. And see, I have told that during convolution operation, here library function takes activation, and there is one thing which is a padding. Padding is actually, I have not shown in the padding actually done to match the features, means if convolution features and convolution in for performing convolution operation, if the input image size is suppose I have considered 8 by 8, so here also padding also needed to extract the 1 by 1 1 by means 1 comma 1 pixel. If you consider, then you have to do padding, because this is not matching the output feature maps of that particular, because the dimension has been reduced and some information also get missed. So padding is necessary. So first of all, convolution, two convolution is done, which is I have considered 64, 64, and then a max pooling done 2 by 2, as I have shown that among 4 they are choosing one, maximizing the pixel value which is the greater among the 4. And then in this way, encoder 4 max pooling done for 4 blocks, and then bottleneck there is no max pooling. Then after that, again decoder upsampling 2D, which is an convolution transpose, and then concatenating the upsampling features and the C4 means block 4 encoder, as I have explained. Then again performing 2 convolutions subsequently, and then in this way, block 7, block 8, and block 9 has been done. Then finally, that I have mentioned you, which is an important part in this unit, to give me a binary marks as an output. For that, last layer, output layer, which is which performing convolution 2D but one operation. It is actually convolution 1D because it gives only an array, and by performing segment activation function, it gives a 0 and 1 value. It gives only 0 or 1. So in this way, binary marks has been generated. Then this is the whole model, as I have shown here, model.summary. This is the model actually is showing through this function dot summary. It gives this kind of output as a chart. Then the defined, I have what I have defined here also, it get recall the suppose load image and marks, it has been recalled to that data loading part to perfectly loaded. If there is any mistake, it will not run, it will give an error. Then after that, I have considered 100 epochs is sufficient, and it giving about 15 to 15 minutes to give me a to perform 100 epochs, and then it got saved as a weights and models both as your .h5 file, which is a file which .h5 represents that file format where the models information and its parameters and its weights has been saved on that particular .h5 file. On the basis of that, I have considered testing operation, because previously up to that training has been done. Means 100 epoch the model has been changed to learn where the in the image where the nucleus is present with means where the nucleus is present through ground truth. I have mentioned it, and model will learn, yeah, this kind of image has this kind of shape of nucleus, whether it is small or large, with particular that image I am providing. With respect to that, I am also providing a ground truth. For that, they will help to extract that particular features through this operation, through this training, and model will learn that here, if any if the model will not learn, then it will not give me an output. So here testing code I have used here. To test a random, I have considered 20 images where I have shown the best result output. Where you can see that the nucleus, the ground truth is this, and the images is this, and it predicting the mask, as unit is giving this as an output, that here is the by giving this image, it giving me this output unit predicted mask, saying and first I think it is a normal and it is an abnormal. So I have shown that abnormal ground truth is likely similar. So testing code, how testing code will be done. First of all, we call the same model unit defined, where the model will pass learn the information, because if I will not call the model which I have been trained, then I can't do a load weights, means to load the weights which have been set as unit weights 100. So through that load weight, we can get all the weights which have been stored, and then give a providing output directory and how to predict and say and how to give these binary marks here. All the things has been shown here, and first of all I have to save it. To save it, I think I have done here. If image per no JPG image found image per 20, yes, I have considered 0 to 20. That's why I have at sorry 21. That's why the range is 20, and uh, in that particular name, due to the date, it has not been shown. The baseline image path as same as the input image name is setting just before that it saving as predict marks. Okay, in this way the testing has been performed, and I have done the visualization result of that testing sample, and it gave me a better at 100 epoch. And this is my references here. I considered two paper on the basis of that I have taken information, and here I am ending actually. Uh, so any questions regarding that, regarding unit? Hello.
So please, any question? Devojit, Devojyoti, Antara, Arnav, Majidul. So thanks, Shashwato,
Okay, sir.
and for this demonstration of the some hands-on practical because of the online mode, virtual mode. So I think this kind of that is demonstration will help the students. So now we are going to our next session. In the next session, we'll start 4:30. Is it a new link or Shashwat, is it a new link or it
It's,
is the
it's
same
a new link, sir.
new link? So we are going to the new link, and now we will see the differentiation between the normal and abnormal cells using MATLAB. So please uh, click for the next session. Thank you all.
Thank you, sir.
Hello, hello. What's up?